In this video, we're going to look at the behavior of charging capacitors. I'm going to introduce you to a set of equations that describe things like charge on a capacitor at any given time, voltage across the plates of a capacitor at any given time. The more interesting thing about these equations is the derivation of them, but this is outside the scope of Physics 2, this Physics 2. If you're interested in the derivation, you just need a little bit of differential equations and a little bit of calculus. There's a video on how to derive these on my 1610 playlist, so if you just want to backtrack to the home of the channel and find that, you can. But in this video, we're just going to talk about the equations and what they mean and how to use them. So here you have a system consisting of a battery, an EMF, a capacitor, and a resistor. We know that when I complete the circuit, if the capacitor is uncharged, it will begin to charge. That is to say, there will be a current that runs through the resistor and starts to deposit charge on the capacitor. We know that it's going to charge up to some maximum value, and we know that the voltage across the plates of the capacitor, when it's charged, will be equal to the EMF of the battery, at least in magnitude. The polarity will be reversed, but we're going to get a voltage across the plates in magnitude equal to the voltage of the EMF. So let's remind ourselves of a couple things. The definition of capacitance is charge per unit voltage. In this case, for voltage, I'm going to use the EMF E here, so I can write Q over the script E. That means the maximum charge is C, the capacitance times the voltage of the battery. I'm writing max here. Usually when we did capacitor problems, I didn't bother to write max because they charge up to some Q, and that's what I'm concerned about. That's what this Q is, but now I'm actually looking at the charging process itself. So the charge will change, and so I'm just denoting this as Q max to remind us. Let's also recall something about current and voltage. Remember, Ohm's law says V is equal to IR. In this case, that's going to be the EMF equal to IR. And what that means is that if I solve this for the current, I get the EMF of the battery over R. Now, we haven't had to talk about this in the context of current yet, but the current here is going to change. Remember, what is the current doing? Depositing charges on the capacitor. As the capacitor gets charged, it becomes harder and harder to do that, so the current will drop. So this is going to represent the current immediately when it starts flowing. So in other words, this is the maximum value of the current coming out of the battery. Right when I close the switch, before there's any charge on the capacitor, this is what I find. But it goes down from there. It starts here, and it ends up at 0. That's different than the charge. The charge starts at 0 and ends up here. All right, so because of the charging process, I should call this I max. So we start here and go down, but for the charge, I start at 0 and go up to here. All right, so we know that the charging is not linear. As I get more and more charges, it gets harder and harder and harder to put more charges on it. It turns out, if you run the experiment and take measurements, it's exponential, as in having to do with the exponential function. Many of you probably saw exponential growth and maybe decay in algebra when you talked about compound interest, or maybe you talked about exponential growth of populations in a biology class. That's the function we're talking about. It's usually denoted with an E. It's just a mathematical constant like pi, although exponential functions are going to be e to the x, it could be e to the negative x, something of this form. Here, though, we are worried about how this changes in time, so this general form is going to show up for us as something involving time in the exponent. I'm just reminding you what exponential functions deal with. All right, so let me give you the equations and then we'll talk about them. Like I said, we're not deriving these, we're just talking about what they mean. So it turns out that the charge on the capacitor as a function of time, and the standard way textbooks do this, yours is no exception. If we're talking about a changing quantity, well, use a lowercase q. So some people have asked, what's the difference between the lowercase q and the uppercase q? In many cases, there is no difference. But in this case, we're using the lowercase q to denote that this is a function of time. It's changing. So it's going to charge up to some q, which I will denote with a capital Q. That's going to keep me from having to write max. So when I write capital Q, that means the maximum Q. I'm going to do the same thing with current. I'm going to write a lowercase I as a function of time. And at its maximum value, that frees me to use the capital for the max. So this is something that's changing in time. But if I write the capital I, that's understood as I max. All right. So the Q as a function of time is equal to Q over E, right? And you say, well, hang on. No, sorry. C, E, looked at the wrong line. Now, you might look at this and say, hang on, that's the maximum value. This can't be at all times. And you're right, this is a coefficient multiplier. What are we multiplying this quantity? 1 minus E to the negative T over tau. And we're going to talk about what that tau is. But first, let's see if this matches up with what we know of the charging process. I know that it starts off at 0 charge on the capacitor if I'm charging it. And it ends at CE. So what happens at t is equal to 0, right? That's when it starts off. So if I look for the charge at t is equal to 0, right when I flip the switch, here's where I plug in t. I'm going to plug in 0, and I'm going to get e to the 0th. Anything to the 0th power is just 1. So this parenthetical expression gives me 1 minus 1, 0 anyway you slice it. Then 0 times this quantity gets you 0. So that actually works. If I plug in 0 for t, right when I flip the switch, I get the charge on the capacitor is nothing, just like I should. After a long time, when t gets really big, right, t here gets really, really big, so I get e to the negative something really large. That is approaching 0. E to the negative something really big approaches 0. So what do I have then? I get 1 minus 0, which is just 1, times CE, which is my maximum charge. So what this says is after a long time, I charge up to CE, the max charge. Exactly like what I know should happen, so it seems like the math is describing the physics pretty well, so I'm pretty happy with that equation. Now let's talk about tau before we move on to the current. Tau is what's called the time constant, sometimes called the characteristic time. It is defined as the resistance of the circuit times the capacitance of the circuit. So sometimes you will see this equation written T over RC. There's no difference between those. This is just a handy way to keep track of the characteristic time of the circuit. Characteristic time means that after one of these things, the capacitor has charged up to about 63%. After, it's a little bit more than that. After, should be an F in there, after 1 tau, whatever tau is, the capacitor is at about 63% of its final charge. If I start there and go 1 more tau, so this would be after 2 tau, the capacitor has charged up about 63% of whatever was left. All right, so if here's the max charge and here is 0, 63% looks to me to be about right there. After 1 tau, I've charged up that much. Now look at what's left. 63% looks to me about right there. After 2 tau, I've charged up that much. And then 63% of that, what's left is there. After 3 tau, looks like I've charged up that much. And so on and so forth, right? Now, mathematically, of course, this never reaches full charge. We asymptotically approach the full charge. That's what exponential functions do. What we have to do then is realize that the math is just describing the physical process, and it's describing it continuously. The exponential function is a continuous function, but what we're actually doing is pasting discrete charges onto the capacitor. So once I get to the tail end of this thing, when I just have a few charges left, the math doesn't describe it particularly well, and I have to remember that what I'm actually doing is putting on one charge, and then another charge, and then another charge, and finally I actually do reach the maximum value. But as long as I'm not looking right at the end of this process, this equation describes this pretty well. So it's a pretty good approximation. That's the characteristic time constant tau. Again, sometimes you'll see this written with an RC in the denominator. It's the same thing. This is handy though, because these are the macroscopic characteristics of our circuit. We choose the resistance, we choose the capacitance by the components we put in. And so this enables you to tailor make a circuit to whatever you need it to be for. This is why RC circuits like this are frequently found in timing circuits. They are good for keeping track of certain increments of time, because this time constant, the characteristic time, is user selectable. We choose these components and put it. Okay, so that's what tau is. I think we've seen what the charging equation looks like. In between the two extremes, in between t is equal to 0 and t is equal to something very large, you put in whatever time you want, or whatever time you're given, and that will tell you how much of the charge is on the capacitor at that point. All right, the current is equal to E over R, and again, that's your max current, right? That's what you get right at the first, times this expression, E to the negative T over tau. So just the straightforward differences here is, if I look in the parentheses, this is a 1 minus that, and this is just the exponential function. That has the effect of flipping the effect, right? This starts out at 0 and ends at the max value. This starts out at the max value and ends at 0. Notice when t is 0, in the parentheses, I just get 1. E to the 0th is 1. 1 times ER is my maximum value. So right when I flip the switch, I get the full current, just like what I said I should. No charges on the capacitor yet, so there's nothing to resist that current. So as time progresses, this expression gets smaller and smaller. It goes from 1 and approaches 0 as t approaches infinity. So as time goes on, the current goes down to 0, which is what we know it should. When the capacitor gets charged, the current stops flowing, right? Fair enough. So that's the charge and the current as a function of time. One more thing you can do with it, you can talk about the voltage as a function of time. And this is the voltage across the plates, right? The voltage of the battery, we're going to assume, doesn't change. But I do know the final value, at least in magnitude, of the voltage across the plates. It will match the battery. That's when the charge stops flowing. That's one of the ways we can think about why the charge stops flowing, because the voltage across the plates directly opposes the voltage of the battery. So I can characterize this as the max value, which is just going to be E times 1 minus E to the negative T over tau. And the behavior of this will exactly match the charge. That should make some sense though, because the charge and the voltage have to be directly proportional. This is the max voltage. This will give you, as it did up here, it will give you 0 at t is equal to 0, so I have no voltage on the plates, across the plates. This will give you 1 at t is equal to something large, which just tells you that after charging, the voltage across the plates is equal in magnitude to the EMF of the battery. I should also point out, if this is true, where'd it go? I didn't solve for it. If this definition of capacitance, what this means is that V is equal to Q over C, right? Q over C, if I divide this expression by C, I just get E, the C goes away, which matches up with this expression. So these two expressions, Q of T and V of T, actually match up very nicely with my definition of capacitance, which of course they have to.